Hello and welcome. In today's lesson, we are going to be exploring the idea of energy and how it relates to something called a photon, a little packet of energy that electromagnetic radiation uses to carry energy from one place to another. Before we begin though, let's start with some thought-provoking questions. So, have you ever thought about why does the tar on a road get hot when the sun shines on it? Maybe you've noticed it on a hot summer's day walking that the road gets very warm. Well, the answer lies in energy, right? Energy is being transferred to the tar road from the sunlight. But maybe we need to pose another question. Maybe you've seen some of these digital thermometers around at the shops and wondered, how does a digital thermometer actually work? Once again, the answer lies in energy and being able to read the amount of energy or absorb a certain amount of energy and have something happen. But let's go to our concept map to explore these ideas further. So as part of our discussion on electromagnetic radiation, we have already examined how electromagnetic radiation behaves like a wave, how it acts like a particle. We then went on to unpack how it propagates through space. We talked about how fast it travels. Remember, we said that it travels very quickly at the speed of light. We then explored the fact that it was a spectrum made up of various frequencies. Now we can finally take all of these concepts and link them to this idea of energy and see if we can link any of the features of electromagnetic radiation like frequency to the energy of the electromagnetic radiation. All right, so we're going to be looking into how much energy is propagated by electromagnetic radiation. Before we do that, though, we're going to need some key words to help us understand. Our first key word is quantum. And a quantum is simply a small packet of energy that cannot be divided into a smaller packet. Think of something that literally cannot physically be divided, like, say, an electron. We don't get more or less than one whole electron. Our next key word is one we've used before, energy. And we know that energy is simply the currency by which things change in our universe. Our last word that we need to be familiar with is constant. One that's quite common in mathematics, but also in physics. A constant is simply a variable that always remains with the same value in every equation that it is used in. So now we've got these key words to help us along the way. We now can start to unpack this idea of what a photon actually is. So what is a photon? A photon is simply a quantum of energy. Remember from earlier we said that a quantum is a small, indivisible amount of energy. So when we talk about a photon, we are referring to a quantum of energy, a small packet of energy associated with electromagnetic radiation. But this poses another problem. If it's a packet, does it behave like a particle? Well, this question has come up a few times already in our investigation into electromagnetic radiation. So now we need to unpack this idea further in terms of what a photon is, to see if we can work out whether it is a particle or does it behave more like a wave. So what is a photon? We've already said it's a small quantum of energy, but what's also important to note is it has no mass, all right? So it's not like many particles we've looked at before. It's quite unique in that it has no mass, and it also has no charge. Now, if it has no mass and no charge, how can we truly say that it's a particle? Does it then behave more like a wave? Well, the question's come up again, hasn't it? We need to examine whether a photon has properties of either a particle or a wave to get a clearer picture on the answer. So let's have a look. What else do we know about photons? Well, we can say that we already know that photons are associated with electromagnetic radiation, and this means that they travel at the speed of light. Remember, the speed of light is given this symbol c, this very large number and value, 3 times 10 to the power of 8 meters per second. If you recall from our last lesson, at the moment, we're pretty sure that light is as fast as anything can go. So now we are posed with the question, when can we describe the behavior of a photon as a wave, and when can we describe it as a particle? Now, to further unpack this, we need to really have a look at the properties of waves that we've already examined and the properties of particles we've already examined in the context of what we now know about photons. So we're asking the question, is it like a wave or is it like a particle? Well, photons travel in straight lines, and they are able to diffract through openings. Whoops, accidentally opened the menu there. This is definitely a property of a wave, one of the ones we looked at as the very first properties of waves. And the diffraction through an opening is also a property of a wave. In addition to both of these wave properties, it's also observed that photons can undergo interference, just like, once again, the waves we looked at earlier. Now, these are all properties of waves, but does this guarantee that photons are always waves? Do they maybe have some particle properties? That idea of particles diffracting when passing through an opening is part of a very famous experiment called the double slit experiment. If you're interested in learning more, you should go check it out using some online resources. But for now, let's quickly look at how photons behave like particles. So still working with the question, is it a wave or a particle? But now, much like many particles we are already familiar with, photons are also easily able to be reflected. Oops, opened the menu again there. They are easily reflected off of surfaces. And sometimes, when particles have a lot of energy, we know that they are also able to penetrate materials. Now, we need to examine whether photons or how photons are able to do these two things as well. So let's investigate further and see if there's some more information. So which photons are able to be easily reflected? Those photons of radio waves, both AM and FM radio waves, are easily reflected. So are infrared photons, as well as the photons of visible light. But what do these all have in common? What can we say we know about them? What can you remember about these three types of electromagnetic radiation? Do you recall that all of these have the longest wavelength? Do you think there's some relationship here between the reflectiveness and the wavelength? Let's keep looking. Now we need to ask which photons are able to penetrate materials, i.e. which are able to behave more like a particle. The photons of UV radiation, like that produced by the sun, X-rays, like those used by medical doctors to look inside us, and gamma rays, those very dangerous ones that are also used in medicine, are all able to penetrate materials. But again, we ask ourselves, what do they have in common? Do you recall that all of these types of electromagnetic radiation have very high frequencies and that means they deliver a lot of energy per second to whatever they're impacting. Let's look further to see if we can unpack this relationship. Looking at a diagram of the spectrum of light or electromagnetic radiation, we can see that our AM radio signals have frequencies that are relatively low in comparison to the electromagnetic radiation produced by radioactive elements. You can see the frequency is 10 to the power of 5 for AM radio waves and 10 to the power of 20 for those radioactive elements. Similarly, we can see that the wavelength of AM radio waves is very large, but as we move across the spectrum, our radioactive elements have extremely small wavelengths. So is there some kind of relationship? Well, we know quite a bit about these types of electromagnetic radiation in general, and we can see that some types of electromagnetic radiation have high frequencies and low wavelengths, and some have large wavelengths and very low frequencies. So what's the relationship to energy? Let's go further. But before we go further, let's pause for a short ad break.